Let's talk polynomials with other zeros. First, I want to talk some just terminology for zeros. Zeros can come in a lot of shapes and forms. The first one is rational zeros. These are ones that we're kind of more used to dealing with. These are going to be just fractions or whole numbers, integers. So a couple examples would be like 1/2, -2, 3/4, okay, -5, something like that, okay? Anything that can be written as a fraction. Irrational zeros are numbers that can't be written as fractions. So some examples of irrational would be those square roots that we've been seeing sometimes, okay, like square root of 2, square root of 10 even. But you also have some irrational numbers that you may have seen before, like pi. That's an irrational number as well. And then we have complex zeros. Complex zeros are our imaginary numbers, okay? So they are typically written in the form a plus bi, but oftentimes we have seen them so far as just like 5i, okay? Or -2i. But sometimes you'll see it as 3 plus 4i or 7 minus 6i. Those are all examples of complex zeros. Now, when I'm talking about polynomials with other zeros, the two things that I'm talking about that are classified as other are irrational and complex. So again, our kind of regular zeros are rationals. Everything else, our irrational and complex, are going to be considered our other zeros. So let's talk real quick about those other zeros. You have seen this a little bit already when we did square root property. Just a quick aside. Remember when we would do like x squared equals like 16, let's say that, and we did the square root of both sides, and then that made it x equals plus or minus 4, and you got two different answers. If I made that -16, what would that be? If I made that -16, that would be plus or minus 4i, right? If I made that square root of 3, that would be plus or minus square root of 3. So you can see that in a lot of these cases, they come in pairs. You're not going to just have one. You could have, or you're going to always have two. When do they always come in pairs, though? That's for the complex and irrational zeros. So they come in what's called conjugate pairs. Conjugate pairs means you got the plus version and the minus version, or the positive and the negative version, okay? So here's a quick example. If a zero is -3 plus 2i, then the conjugate of the zero is, the sign that you're changing to find this is the sign right in front of the I. So this would be your plus minus right there, okay? So this would be, our other version would be -3 minus 2i. So all you're doing is changing the sign in front of the I there. And that makes your pair. Those are two zeros. In a similar way, 3 plus square root of 2, this is going to be where your plus minus is. So this would be 3 minus square root of 2. Okay? So basically it's just saying, hey, you can't have one without the other when it comes to complex and irrational. Rationals, on the other hand, do not have to have a pair. They don't come in conjugate pairs. You can just have a 1 and that be the answer. It doesn't have to have the -1 version with it. Okay, so a quick note on that. So let's look at these two examples here. If -2, 4 minus 5i, and 1 plus square root of 11 are zeros of a polynomial of degree 5, find the other zeros. Okay, degree 5 in this case is saying that you have the highest x or exponent for your variable would be x to the 5th. So you've got a polynomial x to the 5th, and if you go back and look at some of my other videos, you'll see, and we've talked about, oftentimes that highest exponent tells you how many answers you have. And that is actually the case in this. You can have up to 5 answers, but we're actually going to have 5 answers here. How do I know that? Because this -2 is rational. It doesn't have a pair. Okay, but what about this 4 minus 5i? Its pair would be 4 plus 5i. So the other zeros here are 4 plus 5i. And then the other one, 1 plus square root of 11, would be 1 minus square root of 11. And if you look at how many we have, we've got 1, 2, 3, 4, 5. That gets us to that degree 5 that it's talking about. Okay, we have a similar thing in our next example. If 3i and negative square root of 5 are zeros of a polynomial of degree 5, find the other zeros. Again, we're not looking at the rational to give us our other zeros because rationals don't come in pairs. But our I is irrational. No, complex. Sorry. It's complex. I was right the first time I said that. The I is complex. And so it's going to come with a pair. So technically there's really a plus minus in front. It's already got the plus. We need the minus. Let's look at negative square root of 5. This is irrational. Okay, so we've got our negative. We need our positive. So we're going to have square root of 5. And that gives us 1, 2, 3, 4, 5 answers for a degree of 5. Now, why do you need to know all this? Okay, because when we are factoring polynomials or looking at zeros of polynomials, the zeros may not always be rational. We've worked a bunch of problems now where they were, and that's great. But they don't always work out like that. Sometimes, and you've seen in other equations in this course, where we got answers like square root of something or had i's in it, okay? So you've got different options, and we haven't talked about the square roots and the i's when we're looking at higher order, higher degree polynomials, something higher than a quadratic. So now's the time to do that. Let's look at our first example here. Find the rational zeros and then the other zeros of the polynomial function. That is, solve f of x equals 0. So we have our rational zeros here. We have our function here, x cubed plus 5x squared plus 9x plus 45. We're going to do this the same way that we would work any factoring a cubic. Now, there is some tricks to this, but I'm not going to tell you till we finished all of this, okay? And so, again, we're looking at our last number, p is what we called that, and we're listing all the possibilities of p. So we're listing of all of our possible rational zeros here. So for 45, that would be 1, 5, what else? 9. Would 3 go into it? We didn't even try that. 1, 2, 45 divided by 3. Yeah, 15. 5. And then what would that give us? 5, 6, 7, 8, 9. And then 15. And then 45. Okay. Probably not going to be 15 and 45, but you never know. And again, these are all plus minus for each one of these. So we don't know which one's going to actually work. We've got to sit here and figure that out. How are we doing that? Synthetic division. So we're going to start with 1 in the box. And we're grabbing all of our coefficients in our function. That's just a 1 in front there. So this would be 1, 5, 9, 45. I'm writing kind of small because I think we have to try a few of these. Also, I am going kind of quick with a synthetic division. Feel free to pause at any point if you need to. But it is to your benefit to practice synthetic division enough times where you can be quick with it, okay? Because you're going to do it a lot in this unit. All right, all that said, bring down the 1. 1 times 1 is 1. 5 plus 1 is 6. 1 times 6 is 6. 9 and 6 is 15. Add 15, and you're not going to get 0. So 1's not it. Let's try negative 1. 1, 5, 9, 45. Bring down the 1. Negative 1 times 1 is negative 1. 5 minus 1 is 4. Negative 1 times 4 is negative 4. 9 minus 4 is 5. Negative 1 times 5 is negative 5. That's not going to give me 0. Let's try 3. 1, 5, 9, 45. 1, 3 times 1 is 3. That's 8. That's 24. This is getting too big. It's not going to be 3, okay? And so, quick hint on this. Notice that all of these are positive. It's not going to be a positive in the box because then that makes whatever you're doing here get bigger and bigger and bigger. So, that only works with all positive here. So just keep that in mind, but it's going to be a negative answer. So that said, let's try negative 3 and see if that works, and we'll keep that in mind as we go forward. Okay, so this is going to be 1, 5, 9, 45. 1, negative 3 times 1 is negative 3. 5 minus 3 is 2. Negative 3 times 2 is negative 6. 9 minus 6 is 3. Negative 3 times 3 is negative 9. Still not working. But I'm not going to try 5, right, because it's positive. So we're going to do negative 5. That's 1, 5, 9, 45. 1. Negative 5 times 1 is negative 5. 5 minus 5 is 0. Don't panic. Use the 0. Negative 5 times 0 is 0. 9 plus 0 is 9. Negative 5 times 9 is negative 45, and we do indeed get a 0 here. Okay, so negative 5 is a 0. Now, our quotient might be a little funky here. Let's figure that out when we cross that bridge. So, in our answer, we have the rational 0 is. Well, our rational 0 is this negative 5. So, we already know that. Let's write our function. If the 0 is negative 5, what's the factor? The factor is x plus 5. Remember, we're changing the sign and putting it with an x. Then, what is our quotient? That one's a little tricky. So we've got 1x squared plus 0x plus 9. Okay, let's simplify this and put it in that parentheses over there. This would be x squared plus 9. Okay, this is not fully factored, but we haven't really talked about how to factor that. So what we're going to do is kind of work a little backwards and find the 0 first, then we'll work backwards to find the factor. So we're going to set x plus 5 equals 0. Don't really have to do that because we already know it's going to equal negative 5. But then we're going to set x squared plus 9 equals 0. This is very similar to what I just talked about a minute ago. So we're going to move the 9 over by subtracting. That's x squared equals negative 9. And we are taking the square root of both sides to put plus or minus square root of negative 9. Simplify square root of negative 9. So what does that simplify into? Remember, the square root of 9 is 3, but the square root of that negative, or negative 1, is I. Okay, so we get two answers here. 3i, negative 3i. And should it work out that way? Yes, because we talked about just a minute ago this having conjugate pairs. This is a complex answer, so we want this to have the positive and the negative of it. So our quote-unquote other zeros are 3i and negative 3i. Now, again, I don't have the factored form yet, so we're kind of finding the zeros here and working backwards. So if I said what is the factored form of this function, we know the factor for negative 5. That was x plus 5. I want you to think about the 3i in the same way. If that I wasn't there and you just had 3, what would you write for your factor? You would write x minus 3. It's the same thing, you're just putting an I with it. Okay, same thing here. If you just had negative 3, your factor would be x plus 3, but you need the I with it. And that becomes our factored form. X plus 5, x minus 3i, x plus 3i. Okay?